The code is saying that, okay, you can, using this strain compatibility approach, by fixing x and angle of your x, you get one point. Like that, you generate family of point and you can get your surface, which is your three-dimensional surface, like what we are seeing here in this slide. Okay, but it is difficult for us to estimate. So what the code is saying is they are suggesting this load contour method. As we have seen, the load contour method gives an interaction between bendings. Okay, so now let us look at this equation, which is given as mux by mux1 to the power of alpha n, and muy by muy1 to the power of alpha n should be less than or equal to 1. So here I'm not having P directly coming here. So P, the level of axial compression come in the form of alpha n. We will see what it is. Okay. So depending, okay, so we are looking at only for a particular P value, how the interaction is happening between two bendings. Okay. Now what is MUX and MUY? These are your demand. Okay, from your analysis. Okay. So these are your demand, bending moment about X and Y axis. Now what is MUX1 and MUY1? These are uniaxial bending capacities. Okay, both of them, respective about respective axes. Okay, so MUX and MUY are demand about bending demand about X and Y axis. MUX1 and MUY1 are uniaxial bending moment capacity at the particular level of, this is very important, at one particular P. Okay, so again, so for example, let's look at this case. Okay, where we are having this. Okay, in this case, if you look at it, this is the curve that was given by this equation. Okay, here what is MUX and MUY1? So you see here, this is your at a particular value of your axial compression. MUY1 is a uniaxial bending moment capacity, which we can get from your uniaxial bending moment interaction curve. But you have to choose the value of P. So this is your MUY1. Similarly, at this level of PU, whatever that you get is your MUX1. Okay. So these are uniaxial bending moment capacities at the particular level of your axial compression. So now you see here, this is a, if alpha 1, if I keep it equal to 1, this can be approximated as a line, because these capacities will be given, it will be a constant value, right? So, and if alpha, if I'm taking it as 2, it is going to form a circular curve like this. Okay, so you find that here at high levels of axial compression, this equation takes the form of a circular form. At a very low levels of axial compression, this can be approximated as a linear equation. Okay, so for example, here in this case, okay, so this can be idealized as a line. Okay. Similarly, at intermediate levels of axial compression, this equation can be, the alpha n is going to vary between 1 and 2. Okay, so that's how we are saying. So what is, again, this is a failure curve, that what we are going to, failure curve equation between bending moments about both axes. Okay, so if I know my demand, let's say MUX is 100 kilonewton meter, MUY is, let's say, 150 kilonewton meter. Okay, so if I'm able to find these capacities, let's say I'm dealing square column with a symmetrical reinforcement. So MUX and MU1 will be same. Let's say this is about 300 each. Okay, about both axes, they will be same square column. So you plug in this, these are your demand, okay, 100 and 150, these are your capacities. So if I estimate that, if I put it in this value, and now only to use this equation, I need to know alpha n. So to alpha n is function of your PU by pure compression capacity. So which we will see in the next slide. So this also I will be able to calculate alpha n. So you plug it into this equation, then you will get an idea whether your demand is within the surface, okay, here like this, but not outside the surface. So that is an idea that this equation is giving for a particular level of axial compression. So again, so this is based on Bressler's formulation. So he approximated how the interaction between two bendings are going to happen at a particular level of axial compression. So he proposed this equation, and that is able to conservatively quickly tell whether particular demand is meeting the is it safe or not. Okay, so if this plugged in this equation value, if it is less than 1, those demands are actually within the surface. Okay, so wherein approximate relationship between the MURX and MURY for a specified value of PU is established. Okay, now again, what is alpha n? We have discussed this. It is a constant which depends on the factored axial compression PU, and which defines the shape of this load contour. Okay, so that's why we call this as load contour. This equation is called as a load contour because alpha n is going to, the shape of this interaction between two bending moments is going to change depending upon what is the level of your axial load. That is the reason it is called as a load contour method. Okay, because alpha n is going to be function of your PU. In fact, it is going to be function of PU divided by pure axial compression capacity, which we will see. Okay, so this is a very approximate way of checking whether your bending demands are meeting the requirement, right? So let us see. Now, this is what is the Bressler formulation. Now, let us see what is MUX and MUY. We have already discussed that MUX and MUY are factored biaxial moments. Okay, these are your demand. Okay, so these are your demand from your analysis. Okay, for the assumed gravity load and lateral loads, you do analysis and you get your demand for a particular cross section like this. Okay, and then MUX1 and MUY1, they denote the uniaxial bending moment capacities with respect to the major and minor axis under an accompanying axial load. So that means MUX1 and MUY1 are not fixed values. It depends upon what level of axial compression at which you are calculating your uniaxial bending moment capacity. So this is what we said. Okay, if you go back, okay, if I take again, so if I take, let's take, let me erase this. So if I take at this level, okay, axial compression, this is your MU, let's say X1, and this is your MUY. If I take at this level, this is going to be your MU Y1, and this is your MU X1. So you see now the values are changing. So if I take at this location, then this is your MUY1 and this is your MUX1. So depending upon the axial compression, we have seen that in your moment curvature analysis also, right? If I keep changing my axial compression, the ultimate moment capacity is also going to change. We have seen that at low levels of axial compression, the bending moment capacity increases, but when I keep on increasing axial compression, the bending moment capacity will start decreasing, right? So that is what it is saying. So again, uniaxial bending moment capacity is also for a particular cross section is function of what is the axial compression that is acting at that particular cross section. So that's what we are seeing, right? And again, so MUX and MUY are measures of load effects due to external loading, and MUX1 and MUY1 are inherent resistance of the column capacity. These are uniaxial bending moment capacities about both axes for a particular level of axial compression, right? Now we see that for low axial loads, people are using strain compatibility approach again by fixing XU and fixing an angle of XU. You can find one point like that. You generate family of point and develop that surface. Now with using Bresler's formula also, people have found that at low axial load levels, this interaction, okay, is closely resembling if I take alpha n is equal to 1. Okay, or in other words, for low axial compression load levels, the load contour can be approximated as a straight line. So it will become a linear equation, right? And for high axial compression load levels, the load contour is approximated as a quadrant of a circle. So alpha n becomes 2. So that is what, again, we go back and look at this. Okay, so this is your circular. Okay, and this at low values, which we take that as linear. Okay, so When it is in between, then you take alpha n between 1 and 2. So at high levels of axial compression, this interaction between two bendings are going to take the circular form. At low levels of axial compression, it is going to take a linear form. And for moderate axial compression values, alpha value is taken between 1 and 2. So this is the procedure. Okay. Again, just like what we did for uniaxial bending, here also I can generate the entire surface, but there are some challenges and it is a little bit more involved, the calculation procedure. So what are the things? I have to fix XU and also I have to fix the angle of XU. Then you get one PU, one MUX, one MUY, right? Similarly, I repeat the process to generate family of surface. Then I can get a family of points to generate the failure surface. That is a strain compatibility approach, right? But for a design purposes, what we can do is we can use this load contour method to quickly see for biaxial bending whether the chosen dimensions and chosen reinforcement configuration is satisfying the requirement or not, right? Okay. Now, for let's see what the design process is. Okay, so the factored moments acting on the column section with respect to bending about major axes and minor axes can first be resolved into a resultant bending moment mu, which acts about an axis perpendicular to the or inclined to the two principal axes. So, how do you find the resultant bending moment? You take square root of mu x square plus mu y square, and then you can also find out the resultant eccentricity, which is mu this whatever the resultant bending moment divided by the axial compression. Okay, so now design the flexural strength with respect to major axis, uh, assuming this like a uniaxial bending. Okay, so what is in here? Mu x1 is design flexural strength with respect to major axis union bending moment, and mu y1 is design flexural strength with respect to the minor axis under uniaxial bending. So once we got this bending moment, okay, and you have mu now and pu. Okay, so for this, what we can do, I can go ahead and find out what is the area of steel that is required, right? Once I fix my area of steel, then I can also find out for this particular cross section with particular steel, what are the uniaxial bending moment capacities, mu(x1) and mu(y1). Okay, and we will run through an example. Either we can establish our own interaction curve like what we have discussed in the previous module, or I can use the design aids provided by SP16, which is a design aid for IS 456. Already there are ready-made charts that have been developed. Okay, briefly we discussed in the last part of the lecture how to derive this non-dimensionalized curves also. Right, it is very similar to what we have done in the last part of the video. So anyway, so if you look at it. Now, to use this equation now, basically I want to use this equation, right? So for a particular cross section, let's say this cross section, I'm just giving an example. Let's say I'm taking 400 mm by 400 mm, okay? And then I have some steel, okay? And I'm telling that I'm having, let's say, four numbers of each one of them is 25 mm diameter bar, okay? So all these things are given to you, and I'm also saying that FCK is 40 megapascal. Now for this particular cross section, I need to calculate, and I'm also giving you demand. Okay, PU is this, MUX is this, MUY is this. Okay, these values are given to you. Now, how do you use this load contour method? These things are given to you. Okay, now I need to find MUX1 and MUY1. I also need to find what is alpha. Okay, so that's what we are looking at now. The code is saying that if I'm looking at one in the planar view, the shape of this surface, okay, is going to resemble this. Okay, so this form is going to take this at low level of axial compression. This equation is going to take a linear form. At high level of axial compression, it is going to take the form of a circle, quadrant of a circle. Okay, so that is why here alpha n is equal to 2 and here alpha n is equal to 1. For moderate levels of axial compression, we have to change alpha from 1 to 2. Now, how do we do that? Okay, so code is saying that, okay, it is function of your axial compression. Somehow it has to be normalized to how much axial compression is acting with respect to the pure axial compression capacity. Okay, so how to estimate this? This is kind of pure compression capacity. Okay. So this is the pure compression capacity, right? So that's what we have equation here. So how do we get this equation? So if you go back, we looked at what are the strain condition that we assume to estimate pure compression capacity? Epsilon Cu is equal to 0.002. For epsilon Cu of 0.002, what are the concrete stress? It is going to be 0.447 FCK, but 0.447 is approximated here as 0.45 FCK, and I have to multiply with concrete area. And we found that corresponding to a strain of 0.002 for pure compression. Now the entire cross section is subjected to same level of strain, right? So what would be the stress in the steel? That is going to depend upon what grade of steel that I'm going to have, right? So, but the code is saying that, okay, Fe415 means we saw that it is going to be 0.79 Fi for a strain of 0.002. So depending upon the grade of steel, it is going to change. But the code wants to simplify it, and it is giving us a one value of 0.75 Fi, which is reasonably okay. And again, pure compression capacity, we want to estimate it in a conservative way. So that is why this value is kept as 0.75 Fi, which is very close to what you get in your design stress strain curve. And you multiply by area of steel to get your steel contribution. Again, we have seen in pure compression capacity, which one is going to give more capacity is only the concrete. Steel will give 10, 15, 20, 25% depending upon the amount of steel what you have. But 70 to 75% of the capacity will come only from concrete. So that is why the code has kept it as a relatively simple equation and for estimating the pure compression capacity. In fact, to account for that minimum eccentricity, what the code said, this entire thing was multiplied by zero point 0.9, if you remember. Then we end up with 0.4 FCK AC plus 0.67 Fi ASC, right? But in this biaxial bending equation, the code is saying that anyway you are accounting for this biaxial bending. So again, you don't need to multiply that zero point 0.9 and use this equation for calculating the pure compression capacity, right? Okay. So once we calculate this PUZ, what the code is saying is, if you know if you are given this demand, you divide that by this PUZ and find out what the value is. If PU by PUZ is less than zero point 0.2, okay, then alpha n can be taken as 1. Similarly, in this regime, okay, when PU by PUZ ratio, when it becomes more than 0.8, that means it is level of axial compression is so much, it is almost getting close to that of a pure compression capacity. In that case, the alpha n is taken as 2. In between value, what the code is saying is you interpolate. Okay, if I'm having 0.3, so interpolate between this using this line. Okay, so that's what the code is suggesting. Okay, so depending upon where you are there, you can interpolate. So these are the range up to this alpha n equal to 1. When pu by pz is less than 0.2, alpha n is taken as 1. When pu by pz becomes more than 0.8, alpha n is taken as 2. For intermediate values, you have to interpolate. So that is what the code is saying. So once I know alpha n, I know MUX and MUY demands, and MUX and MUX1 and MUY1 are uniaxial bending moment capacities for a particular level of axial compression. So I know all the things. I can plug it into this equation to see for the chosen dimension and chosen reinforcement configuration whether the design is adequate or not, right? So this is using a load counter method. Another approach is if you have a program using strain compatibility, I can calculate the entire surface and put all the demand, and we have to find out whether the demands are falling within the surface or on the surface also okay, but it should not go outside the surface, right? Okay, so this is the code procedure. So given the demand PU, MUX and MUY, verify these eccentricities, okay, and these eccentricities should satisfy at minimum eccentricities. If EX and EY is less than E minimum, code requires that it is sufficient to consider that eccentricity about one axis exceeds the minimum, okay, or in other words, let's say let's say in both the axes, if it is less than E minimum, then code is saying that okay, you use whatever about one axis minimum value, and about axis another axis you take the minimum eccentricity that is specified by the code. You need not consider minimum eccentricity about both axes if your applied eccentricities are less than E minimum. Okay, because anyway it is like very close to that of pure compression. The applied eccentricity is very low. So code is saying that you consider only the minimum eccentricity about one axis. That is the reason, right? Now, once we know this demand, then I have to assume the trial section per column. Okay, so and then how do you find the trial sections? Of course, your from pure compression, you can estimate the gross area of the section. And how do you get your AS? AS we can calculate using resultant bending moment. How do you get the resultant bending moment mu? Which we can take that as square root of mu x square plus mu y square, and you multiply it by, let's say, 1.2 or so. And then using this as a uniaxial bending moment and axial compression, you can find out A's. So this is a trial section. So I can find out the area and the amount of steel in an approximate way by converting the biaxial bending into an uniaxial bending, and then use uniaxial compression bending interaction curve to find out what is the AS. Okay. Now once the section dimensions are fixed and the area of the steel is fixed, I can calculate my uniaxial bending moment capacities for a particular value of Pu. Okay, and we need to ensure that Mu-x1 and Mu-y1 are significantly greater than Mu-x and Mu-y respectively. Okay, why is it so? Because this Mu-x1 and Mu-y1 are uniaxial bending moment capacities. When you have a biaxial bending, there will be an interaction and the capacity may not be adequate. Okay, so that is why we have to make sure that Mu-x1 and Mu-y1 are significantly greater than the respective demands. Okay, so otherwise suitably we have to redesign the section. Then once we do that, then we find out PUZ, which is your pure compression capacity, and then you know your PU by PUZ can be found. Then from this I can find out alpha n. Okay, so once we find alpha n, then we plug in to your equation and then set. Okay, now let's quickly run through a example problem. Okay, I'm taking a corner column 450 mm by 450 mm, and you can see it is located in the lowermost story of a system of braced frame, and it is a braced frame, right? And subjected to an axial compression of 1500 kilonewton. Bending moment x-axis about x-axis is 300 kilonewton meter. Bending moment about y-axis is 160 kilonewton meter. Unsupported length is 3.5 meter. And you can take concrete grade as M30 and steel as Fe500. Let's see now how do we go about the process. Okay. First is we need to check minimum eccentricities. Now what are the applied eccentricities? Moment divided by mu. Let's say Ex is going to be in this case, it should be the other way around. Ey should be this, okay, and Ex should be this, as we've seen, okay. Uh, Ey will be Ey will be bending moment Mu-x, because again, we go back what our convention. When I take bending about x-axis, I have to take, let's say, your Pu is acting here, okay, at this point. So which would be the eccentricity? It will be this, okay. So I have to take Ey, okay. Similarly, if I'm taking bending moment about y-axis, I have to take this as eccentricity, which is Ex. That's why I'm saying My will be Pu into Ex, okay, and Mx will be Pu times E1. So E1 and Ex are 200 mm and 106.67, right? Let us see what are the minimum eccentricities as per the code. We know the formula for minimum eccentricities, L by 500 plus least lateral dimension about the axis of bending divided by 30. Here we are dealing with a square column. So both x and y axis you will have same minimum eccentricities. That works out to be 22 mm, which has to be greater than 20 mm. But you see here, both these eccentricities are lesser, far lesser than applied eccentricity. Okay, so I don't need to really bother and consider this minimum eccentricities. Anyway, the applied eccentricities are much higher than your minimum eccentricity. So there is no modification for demand to be considered. If this applied eccentricities, let's say, working out to be 10 mm, then we need to at least consider 22 mm of bending moment or eccentricity of 22 mm. That will produce bending of PU multiplied by 22 in our design. But in this case, because the applied eccentricities are far higher than that of your minimum eccentricities, I don't need to do any modification. So let's assume effective cover of 60 millimeter. Let's see now how to get your longitudinal steel. Okay, so I'm saying that for this particular load 1500 kilonewton, first I need to convert the demand biaxial bending into uniaxial bending. So I'm taking a resultant as square root of MEX square plus MEY square, and I'm also slightly increasing it by 15-20 percentage and finding the demand. So this section has to be designed for P of 1500 kilonewton and bending moment of 391 kilonewton meter. Okay, so assume this D prime as 60 mm. Okay, now we are going to use SP16 design charts. To use the design charts, you will have multiple categories. Okay, columns reinforced with equal reinforcement on all four sides, columns reinforcement with only on two sides, and then you have different charts that will be given depending upon the grade of steel. And also you will have at the top, you will have D prime by D value. Okay, because to establish those charts, I need to assume what is uh, the the cover that I am fixing. So then only I can calculate the capacities in a non-normalized, non-dimensionalized form, right? Anyway, in this case, if I take D prime as 60 and D as 450, D prime by D works out to be 0.13. But however, if you look at SP16, you will have charts that will be available only for D prime by D of zero point 0.1 and D prime by D of 0.15. Now, in our case, it is coming in between. So then how do we calculate? I take values from both the charts and then I do interpolation. Okay, so that's what we do. So I'll show you in the charts as well. But now let's assume that for a D prime by D of 0.133, the chart gives me a value of 0.095. So what is P by FCK? P by FCK is nothing but P small p is again 100 area of steel by D into D. Okay, and FCK we know 30. So if 0.095, then I can go ahead and we know to calculate this P by FCK, again I need to know what is the demand. So we calculate the small mu demand as mu by FCK BD square, because these are the values that will be used to arrive at what is the area of steel that is required. Okay, so the demand is 391 divided by FCK is 30 and BD square, B and D are same, so I put 450 and I get a value of 0.143. Right, so for a 0.143, if I go back and calculate what is PU, and PU is where again in the to use your design aid, I need to calculate the demand ratios. Okay, which is small PU's axial compression divided by FCKPD, you get a value of 0.247. Okay. Now, using this demand values, I have to go ahead and refer to the charts. In this case, because it's a biaxial case, for a biaxial case, always we need to put reinforcement on all four sides. We are taking equal reinforcement on all four sides. And I'm going to look at both the charts 48 and 49, because this is for 48 and this is from 49, but I need value for D prime by D of 0.133. So I cannot directly use from one chart. Okay, if D prime by D for us, if it works out to be 0.1, I can go ahead and use chart 48, but my D prime by D is 0.133, so I cannot use directly the chart. I have to do interpolation. So after interpolation, we are getting 0.095, let's say 0.0932 is what we are getting. Then we are slightly increasing and then we are putting 0.095, and when you multiply that with respect to, so in fact this small p is uh, 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 basically the area, the percentage of steel PT multiplied by FCP. Okay, rho required. Okay, this is what we said. We got the small p that when you divide by that, then you get, or in other words, this ratio P by FCK is this. So P is nothing but 0.0932 multiplied by 30. So 0.0932, I'm slightly rounding off to 0.095. So the row required is 2.85 percentage. You see columns, this corner column is requiring 2.85, means close to 3%, 2.85% of steel. So again, when I multiply by area divided by 100, I get the amount of steel that need to be provided. Okay, so this is the steel required. Again, we know what is the P rho, this P required 100 AS by BD. Okay, that's why I'm multiplying BD divided by 100 to get what is the steel required. Okay, so for this again for 5,771 millimeter square, this is a biaxial case. I need to make sure that I provide reinforcement on all four sides so that bending resistance about both the axes we will get. So I'm saying always it's uh, we have to put a symmetrical reinforcement. So we are providing 12 numbers of 28 mm diameter bars. So for each 28 mm diameter bar, I get 615 mm square. So when I multiply by 12, I get total area of 7,389 mm square, which is slightly on the higher side. In fact, because I want to keep the symmetrical reinforcement, that's why I need to come up with it. If I'm putting 25, then it may not be just to satisfy. So that is the reason we are putting slightly a conservative steel. So you can also choose two different diameters also. In corner ones, you can choose a slightly a larger diameter, and the middle ones you can choose a slightly small diameter also. So that is also possible. But in this case, we have taken all the bars to be same 28 mm diameter. So to keep the symmetry, I am putting slightly higher steel. Okay. Now let's see. Now let us see how do we get these values. Okay, so we are looking at this d prime by d of 0.10, and this is another chart d prime by d equal to 0.15. Okay, so this is the layout of steel. Okay, for which these capacities have been derived. So what you see here is in the x-axis you have mu by fck bd square. That's what we written that as small mu, and in the y-axis you have pu by fckbd, or in other words, it's basically small pu. Okay, we get these ratios so that we can use the chart. So you have family of charts. So these are all capacity curves for different p by fck value. Okay, so these are valid for particular amount of steel which is normalized to concrete strength what I am using. So in this case, in our case, what was the d prime by d that we got? 0.133. So that is the reason I cannot use either one of the charts directly. I take the values from both the charts and then I interpolate what is the amount of steel that is required. Right. So now let us see. This is the demand that we got. PU what we got was 0.247, and then mu I got a value of 0.147. So they are intersecting somewhere here. So I have to choose a steel P by FCK value between zero point zero 0.08 here and then 0.10 here. So in between, depending upon where you are there, you have to do the interpolation. That's how we end up with 0.092 something, right? From this chart. Now we need to do the same thing for we get the value of 0.085, very close to that of 0.08. So I get P by FCK of 0.085. Similarly, I do the same thing for using this chart of d prime by d equal to 0.15. So I get this, and then for this P by FCK works out to be 0.1. So now I have to interpolate again between these two values. Why? Because this is valid for d prime by d of 0.1 and this is valid for d prime d of 0.15, but what I needed is for 0.133. So I do the interpolation and then we got the value that what was specified in the last slide. So this is how we got this 0.0932, and slightly we round it off to 0.095, and then we got that multiplied by FCK to get your PT, and then you get your steel, and then again we bumped it up just to be on the conservative side. So because I need to also have symmetrical reinforcement layer. That is the reason. Though the required was 5,771, I ended up putting 7,389. But you can also have let's say 8 25 mm bars and 4 28 mm bar. So that combination also will work out to be more attractive combination. In this case, I kept it simple. So we got these values and we did the interpolation. Now what is that I need? To use that equation, that load contour formula suggested by Bresler, what was that formula? Mux by Mux1 to the power of alpha n plus Muy by Muy1 to the power of alpha n should be less than or equal to 1. So to use that equation, I need to know what are the uniaxial bending moment capacities for the reinforcement that what I have provided, right? So let us calculate that. So we have got this PU by FCK BD, which is 0.247. And what is the reinforcement provided is 7,389. And if I convert that into P by FCK, it works out to be 0.1216. Okay. So 0.1216. Now, what is D prime that actually what we are providing? A minimum clear cover of 40, and I'm assuming that I'm going to use 8 mm stirrup. So this is stirrup, okay, like what we have done in com, okay, and this is basically your 20 mm, okay. So in this case, actually, D prime by 2 should be actually right. So it should be actually 28 by 2. Okay, because we are using all 28 mm bar, right? So if you do that, then you will find that uh, this is going to be about 60 mm. Okay, so this works out to be about 60 mm. Because why is that? Now that I have found that D prime is I am using 28 mm bar, right? So it should be 14. It should be right. So if you do that, in fact, this should work out to be 60 48 plus 14. So it should be 62 m. Okay, not 58. This will be 62 m. So again, if you put D prime by D, then you get a value of about 0.128. And now that this has become 62, this will become slightly 0.13. It will become right. Now again, how do we get that value? Now for this P by FCK, and the demand, bending demand, I go back and for this axial demand, I go back and calculate what is mu by FCK. So what we are interested is in finding what is mu x1 and mu y1. That will, those are the uniaxial bending moment capacities corresponding to an axial compression. Okay, now reinforcement is given, axial demand is given. Using the reinforcement and axial demand, I go back and check what is that ME by FCK BD that I can take. That would be the uniaxial bending moment capacity. So again, we are going to use this. So for D prime by D of zero point 0.1, I get the small mu. So what is this? This is your small mu. Okay. So the small mu, how do we define the small mu? Is basically capital mu by FCK B D square. Okay, so that's how we get your small m. Now I use these two charts, 0.1 and 0.15. I get these two values, but I need it for 0.128, or in this case, it will become 0.13 or so. So you can interpolate and you will find that it will be 0.175 or so, right? So once you do that, you can, because this is a square column symmetrical reinforcement. So bending moment, uniaxial bending moment about both the axes will be same, because I have same reinforcement detail, and the dimensions x and y directions are same because it's a square column. When you calculate, you get your capacities as 470.2 kilonewton meter. Right, now we got bending moment capacities, uniaxial bending moment capacities at PU equal to 1500 kilonewton, right? So what is the next thing to use the load contour method? I need to find out what is alpha. Okay, and also you find that this uniaxial bending moment capacity should be sufficiently higher than your demand, which is 300 and 160, because we are talking about interactions. We are not talking about one uniaxial bending. So whatever the uniaxial bending capacity that what I have designed should be significantly higher than your demand. Then only I will satisfy that load contour equation, right? So that we will see now whether we satisfy. So now, just to illustrate, how do we get your the uniaxial bending moment capacity? So what was given to you? P by FCK was given to you. So what was that? If you go back, P by FCK was 0.1216, right? So that was given to you. So and PU by FCK BD was 0.247. So this value was given, 0.247 was given, right? And then this value was given. What was that again? P by FCK was 0.12. So somewhere here. So this value is given. So if I go back to this charts, corresponding to that, okay, so somewhere here, so I this value is given and this chart is given. So I have to go down here and then find out what would be the m u by fck bd square that will satisfy this curve. Okay, so that's how we are finding. So now we are not given pu by fck bd and mu by fck bd square. We are given reinforcement and axial demand. For that, we are calculating what is the bending moment capacity, right? So slightly different. So this is given, okay, 0.247. Now, what was that? This we have to see P by FCK of 0.12 something, right? So if you do that, we are somewhere here. So that's why we are going down here, and then we are getting a demand as 0.185. Similarly, I do the same exercise. Then because this is your P by FCK was given to you, so that is the reason I'm this curve's limit is given. This is given. For that, my mu by FCK BD square is 0.185. Similarly, I do the same thing for d prime by d equal to 0.15, right? So you get 0.162. Again, this is valid for 0.1, 0.15. Now we will need d prime by d equal to 0.13 or so. So again, you do the interpolation and you find out what is mu x1 and mu1. Now we got the uniaxial bending moment capacities. We know the demand. Only alpha n we need. So alpha n, how do we get? First we get your pure compression capacity, which is 0.45 FCK AG or AC plus 0.755 times AC. So you plug in all the values, okay, and this is the area of steel, and this is your total gross area. So because I'm using gross area here, I have to subtract that concrete stress of 30.45 FCK. That's why I'm subtracting here, and you get pure compression capacity of 5,405 kilonewton. Then you take the ratio of axial demand by pure compression capacity, which works out to be 0.277, and you find that it is between zero point 0.2 and zero point 0.8. So alpha n, as per our equation, again, if you remember, when pu by puz is less than zero point 0.2, you take alpha n as 1, and when you pu by puz becomes more than zero point 0.8, you take alpha n as 2. In between values, you have to do the linear interpolation. So that's what we are doing here. Then alpha n works out to be 1.129. So when you substitute now all of them, you find that you get a ratio of 0.898, close to zero point 0.9, which is a reasonably a good optimal design. So if you slightly tweak the design and slightly if you reduce the steel, you can make this getting very close to that of 1. That would be a very economical and optimized design. But in this case, it's a little conservative, but it's not too bad. It is very close to that of 1. So we can say that the reinforcement, whatever that you have provided, 12 numbers of 28 mm dia, is good enough for the demand that are required to be satisfied, right? So now let us look at the detailing, the minimum diameter and maximum spacing, all these things like what we have discussed in the previous parts of the video, they are applicable here as well. Tie diameter has to be less than maximum longitudinal bar divided by 4, which is 7 mm or 6 mm. So I have to use 8 mm tie. So I have to take maximum of these two. So I say that I'm putting 8 mm dia. And in dia, again, in stirrups, we have seen that try to put lower diameters, but not lesser than 6 mm. 8 mm, 10 mm is good. Okay. If you put lesser diameter, you end up with closer spacing. That is also going to be good from confinement point of view. And spacing, again, it should be less than or equal to d of 450 or 300 or 16 times the longitudinal bar 440. Okay, so the minimum is 300. So that is why we are providing 8 mm dia at 300 centimeters. So the reinforcement works out to be just 12 bars, symmetrical, nice reinforcement, and we know that the alternate things also has to be confined. So I can have two links like this. Okay, one link like this. Okay, as a tie. It should be close to tie, right? And then you need to have 4 bars. So this will be good design. All right. So let's summarize. So in this part of the video, we discussed how the interaction surface is derived for biaxial bending. And we also discussed IS code provisions for how to design for biaxial bending. Particularly, we talked about Breslau's load contour method, and we illustrated how to use SP16 and how we can do the design example for biaxial bending, right? So again, these are the references that you can use for further thing, and SP16 is readily available. You can download it from internet, right? And again, the slides for this particular part of the video was prepared by my PhD student Mohan. I would like to thank his effort, and thank you.